Right now, somewhere between Mars and Earth, an object from beyond our solar system is doing something that shouldn't be possible. On October 29, 2025, astronomers Zhichen Zhang and Carl Battams documented something extraordinary. The interstellar visitor, designated 3I Atlas, didn't just brighten as it approached the Sun. It changed color, shifted its entire emission spectrum from red to blue, became several times more luminous. And according to calculations by Harvard astrophysicist Avi Loeb, the object's surface temperature may now exceed that of the Sun itself. Think about that for a moment. An object hurtling through space, supposedly a comet made of ice and rock, burning hotter than the star it's approaching. That's not how physics is supposed to work. And here's the thing that has scientists genuinely concerned. There's no natural explanation for what they're seeing. The timeline matters here, so let me walk you through exactly what happened. On October 27, 2025, 3I Atlas reached its closest approach to the Sun, what astronomers call perihelion. This wasn't unexpected. The object had been tracked since its discovery, its trajectory calculated and recalculated. Observatories around the world had their instruments trained on this visitor from interstellar space, waiting to capture data during this critical window. What they expected was predictable comet behavior, increased outgassing as solar radiation warmed the icy surface, a brightening due to reflected sunlight, and the expanding coma of gas and dust. Perhaps some fragmentation if the structural integrity couldn't handle the thermal stress. Standard comet physics. Textbook stuff. But that's not what happened. Instead, on October 28th and 29th, as Zhang and Battams compiled their observations, a pattern emerged that made no sense whatsoever. The object's spectrum, its electromagnetic fingerprint, was shifting. Not gradually, not subtly, dramatically. The dominant wavelengths were moving from the red end of the visible spectrum toward the blue. Simultaneously, the brightness was spiking, not by percentages, by multiples. The object was becoming several times more luminous than predicted models suggested. And when Loeb ran the numbers, calculating what kind of temperature would produce this spectral signature, the result was staggering. Temperatures potentially exceeding 5,778 Kelvin, the surface temperature of our Sun. The question everyone's asking, what kind of comet burns hotter than a star? Let's back up to what happened before this moment, because understanding why this is so bizarre requires context. 3I Atlas isn't the first interstellar visitor we've detected. That distinction belongs to Oumuamua, the cigar-shaped object that streaked through our solar system in October 2017 and immediately sparked controversy. Oumuamua exhibited its own set of anomalies, including an unexplained acceleration as it departed the inner solar system, acceleration that couldn't be fully explained by outgassing or radiation pressure. Then came 2I Borisov, in August 2019, the second confirmed interstellar object, which behaved much more like a normal comet, reassuring astronomers that perhaps Oumuamua was just an outlier. But 3I Atlas, discovered earlier in 2025, brought the mystery roaring back. From the beginning, this object was different. Its trajectory was hyperbolic, confirming extrasolar origins. Its composition, based on early spectroscopic analysis, suggested a comet-like body with volatile ices. Nothing too alarming initially. Standard interstellar visitor. But Avi Loeb, who had already made waves with his hypothesis that Oumuamua might be an extraterrestrial light sail, was paying close attention. Loeb's credentials matter here. He's the Frank B. Baird Jr. Professor of Science at Harvard, former chair of the Astronomy Department, former director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. Not a fringe figure. A mainstream astrophysicist who simply refuses to dismiss unconventional possibilities. When he looked at the preliminary data on 3I Atlas, he saw echoes of Oumuamua's strangeness, and he said so publicly, suggesting this could be another potential probe from an extraterrestrial civilization. The scientific community largely rolled their eyes. Until October 29th, when the data from perihelion came in. Now nobody's rolling their eyes. They're scrambling for explanations. Here's where it gets weirder, and I need you to understand each layer of this anomaly, because they compound. First, let's talk about the color change. When astronomers observe celestial objects, they're not just looking at brightness, they're analyzing the spectrum of light, breaking it down into constituent wavelengths. Different temperatures and different chemical processes produce different spectral signatures. For a typical comet approaching the Sun, you'd expect to see emission lines from sublimating ices, water vapor, carbon dioxide, carbon monoxide, methane. You'd see a spectrum dominated by reflected sunlight and fluorescence from these gases. The color would shift slightly as different ices sublimate at different temperatures, but we're talking subtle changes in specific emission lines, not a wholesale shift of the entire spectrum. What Zhang and Batams documented was fundamentally different. The continuous spectrum of 3I Atlas, the overall shape of its light curve across wavelengths, was shifting blue. That means the peak emission wavelength was moving toward shorter, higher energy photons. And there's really only one phenomenon that causes that: increasing temperature. Wien's displacement law tells us that as an object gets hotter, the peak wavelength of its thermal radiation shifts toward the blue end of the spectrum. It's why a heating element glows red first, then orange, then yellow-white as it gets hotter. But here's the problem. Comets don't have their own internal heat source. They're heated by the sun. They can only reflect and re-radiate that solar energy. And no matter how efficiently they do that, they can't get hotter than the effective temperature of the sunlight hitting them. That's like saying your car's hood can get hotter than the flame of a torch you're holding above it. It violates thermodynamics. It doesn't add up. Second anomaly: the brightness increase. Comets do brighten as they approach the sun, absolutely. More solar energy means more sublimation, larger coma, more surface area reflecting light. But the relationship is predictable. We have models. We have decades of observations. We know how comet brightness scales with distance from the sun. 3I Atlas threw those models out the window. The observed brightness increase was several times greater than predictions. Not a little bit off. Orders of magnitude off. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury, who has studied numerous comets and trans-Neptunian objects, would likely describe this as statistically impossible given standard comet physics. The amount of volatiles you'd need to sublimate to account for this brightness, the sheer volume of gas and dust, would require the object to be significantly larger than observations suggest, or to be composed almost entirely of highly volatile materials that shouldn't exist in significant quantities in interstellar space. It's like finding smoke without fire. The effect is there, but the cause doesn't match. Third anomaly: the temperature calculation. When Loeb analyzed the spectral data and calculated the blackbody temperature, the equivalent temperature of an object emitting this spectrum, he arrived at values approaching or exceeding the sun's surface temperature of approximately 5,778 Kelvin. Let me give you some context for how absurd this is. The highest temperature ever measured on a comet nucleus was around 400 Kelvin, maybe pushing 450 Kelvin in extreme cases during very close solar approaches. We're talking about surface temperatures hot enough to melt most metals, hot enough to glow white-hot, hot enough that any ice would have explosively sublimated long before reaching this state. And yet, 3I Atlas apparently maintained structural integrity while exhibiting this temperature. That's not just weird, that's physically implausible for any known cometary material. Dr. Konstantin Batygin from Caltech, an expert in planetary dynamics and unusual solar system objects, would almost certainly point out that at these temperatures, you're not looking at a comet anymore. You're looking at something with entirely different material properties, something that can withstand extreme thermal stress without disintegrating. Stop and consider that. What material can do that? What structure? Let's talk about what we do know. And trust me, what we know is already breaking every rule. The observations are solid. This isn't some fuzzy image from an amateur telescope. Zhang and Batams used professional-grade instruments, multiple independent observations, cross-referenced data. The spectral measurements are real. The photometry is real. The object's position, velocity, trajectory are all precisely known and confirmed by multiple observatories. We know 3I Atlas entered the inner solar system on a hyperbolic trajectory, with an eccentricity greater than 1.0, which definitively means it came from interstellar space. We know its velocity relative to the local standard of rest, the average motion of stars in the Sun's neighborhood, was consistent with an object from beyond our solar system. We know it made its closest approach to the Sun on October 27, 2025, coming within approximately 0.3 astronomical units, about 45 million kilometers from the Sun's surface. For comparison, that's inside Mercury's orbit, but not dramatically so. Plenty of sun-grazing comets have survived closer approaches. We know the object's size is estimated at roughly 500 meters to 1 kilometer in diameter, based on brightness and assumed albedo, though that size estimate is now questionable given the anomalous behavior. And we know that as of October 29th, the object was intact, not fragmenting, not showing signs of structural failure, despite exhibiting conditions that should have torn it apart. The spectroscopic data is where things get technical. But stay with me, because this matters. Early observations of 3I Atlas, before perihelion, showed emission lines consistent with water ice, carbon dioxide ice, and possibly some carbon monoxide. Standard comet stuff. The albedo, the reflectivity, was estimated at around 0.04 to 0.06, typical for comet nuclei, which are generally darker than asphalt due to their composition of ice, mixed with dark carbonaceous material. The light curve, the pattern of brightness over time, followed expected trends as the object approached the Sun. Everything was normal. Then, during the perihelion passage, everything changed. The emission lines began to change character. The continuum, the smooth background spectrum beneath the emission lines, started to shift. And most dramatically, the overall spectral energy distribution moved blue. When you plot intensity against wavelength, the curve that typically peaks in the red or infrared for a comet nucleus was moving its peak toward the green, blue, even ultraviolet parts of the spectrum. That spectral peak position is directly related to temperature through Planck's law and Wien's displacement law. You can't fake it. You can't misinterpret it. A blue spectrum means high temperature, period. And the temperature calculations that Loeb performed using standard physics gave results that should be impossible. Let me show you what I mean with some concrete numbers. The Sun's surface, the photosphere, has a temperature of about 5,678 Kelvin. At that temperature, Wien's law tells us the peak emission wavelength is around 500 nanometers, which is in the blue-green part of the visible spectrum. That's why the Sun appears white or slightly yellow to our eyes. It's emitting across the visible spectrum with a peak in the blue-green. For 3I Atlas to show a spectrum shifting toward the blue, with peak emission approaching similar wavelengths, means temperatures in that same ballpark. Maybe not quite 5,078 Kelvin, but potentially 4,000 to 5,000 Kelvin or higher. Now compare that to comets. Comet Hale-Bopp, one of the brightest and most active comets of the modern era, had a nucleus temperature estimated at around 290 to 310 Kelvin during its 1997 passage. Even sun-grazing comets from the Cruiser group, which pass within 1.2 million kilometers of the Sun's surface, experience temperatures of maybe 2,000 to 3,000 Kelvin, and most of them disintegrate. They literally evaporate. The idea that 3I Atlas, at 45 million kilometers from the Sun, could be hotter than those sun-grazing comets, hotter by a factor of 2 or more, is staggering. It defies everything we know about thermodynamics and cometary science. Dr. Jane Rigby, an astrophysicist who has worked extensively with spectroscopic data, would likely emphasize that you can't fake a black body spectrum. It's a fundamental physics signature. When an object emits thermal radiation, it follows a very specific curve, the Planck curve, and the shape and peak of that curve tell you the temperature. You can have emission lines on top of it from specific atomic or molecular transitions, but the underlying continuum doesn't lie. If 3I Atlas is showing a blue shifted continuum, it's hot, really hot, and that heat has to come from somewhere. The sun's radiation at 0.3 AU is intense, about 11 times more intense than at Earth's distance, but it's still just sunlight. It can heat a comet's surface to maybe a few hundred Kelvin, cause rapid sublimation, but it can't raise the temperature to thousands of Kelvin unless something else is happening. Either the object is absorbing energy with impossible efficiency, converting and concentrating it somehow, or there's an internal heat source. And comets don't have internal heat sources. They're inert balls of ice and rock. They don't have nuclear reactions or chemical energy reserves that could produce this kind of heat. That's the paradox staring astronomers in the face. One school of thought suggests that maybe we're not seeing thermal emission at all. Maybe the spectral signature is being dominated by some kind of fluorescence or chemical emission process that mimics a hot black body spectrum. Certain chemical reactions, certain excited states of atoms and molecules can produce bright emission across a range of wavelengths. If you had the right mix of materials and the right conditions, maybe you could create a spectrum that looks thermal but isn't. Dr. Paul Weissman, a senior research scientist who has spent his career studying comets, might argue this position. The problem with this theory is that it's really hard to make it work quantitatively. Fluorescence gives you emission lines, specific wavelengths where particular atomic or molecular transitions occur. You see this with normal comets: bright green emission from diatomic carbon, blue emission from carbon monoxide ions, ultraviolet emission from hydroxyl radicals. But these are lines, spikes, in the spectrum at specific wavelengths. The underlying continuum is still there, and it's still determined by temperature. To fake a hot black body continuum with fluorescence, you'd need an incredibly broad range of emission lines, all blending together from every possible wavelength. That requires an implausible variety of chemical species, all excited simultaneously, all in just the right proportions. It's theoretically possible but stretches credibility. Another school suggests that maybe the object is fragmenting in a way we haven't detected yet, and what we're seeing is a cloud of extremely fine dust particles being released. When dust particles are very small, smaller than the wavelength of light, they scatter light differently than larger particles. This is called Rayleigh scattering, and it preferentially scatters blue light more than red light. It's why the sky is blue. If 3I Atlas was suddenly releasing enormous quantities of submicron-sized dust, that dust cloud could scatter sunlight and create a blue-shifted appearance. Dr. David Jewett from UCLA, who discovered the first Kuiper Belt object and has extensive experience with cometary dust, might support this hypothesis. The numbers sort of work. You'd need a lot of dust, but it's possible. But there's a problem here too. Rayleigh scattering is about scattering, not emission. It changes the color of reflected light, but it doesn't change the brightness as dramatically as observed. And it certainly doesn't explain the extreme temperature calculations. When you do spectroscopy, you're not just looking at color, you're analyzing the detailed shape of the spectrum. A Rayleigh scattered spectrum looks different from a thermal black body spectrum. They have different mathematical forms. The data from 3I Atlas, according to Loeb's analysis, is more consistent with thermal emission than scattering. So while this theory could explain part of the color change, it doesn't fully account for the observations. But there's a third possibility, the one that Loeb has been cautiously suggesting since Oumuamua, and it's the explanation that makes most scientists uncomfortable. What if 3I Atlas isn't a comet at all? What if it's a manufactured object, a probe from an extraterrestrial civilization, and what we're witnessing is intentional activity? Before you dismiss this as fringe science, consider the context. We now know that the universe is teeming with planets. Thousands of exoplanets have been confirmed. And statistical extrapolation suggests there are billions of potentially habitable worlds in our galaxy alone. The Fermi paradox, the question of why we haven't detected any signs of extraterrestrial intelligence despite the apparent likelihood of its existence, has dozens of proposed solutions. But one of them is simply that we haven't been looking in the right way or at the right things. We've been listening for radio signals, searching for megastructures, looking for atmospheric biosignatures on exoplanets. But what if advanced civilizations send physical probes instead? What if interstellar space is crisscrossed with autonomous exploration devices, and occasionally one passes through our solar system? From an engineering standpoint, it makes sense. A physical probe can make direct measurements, collect samples, perhaps even transmit data back using methods we wouldn't recognize. And if you were designing such a probe to survive interstellar space, to function in extreme environments, you'd need exotic materials and energy systems. Think about what that means. An object designed to travel between stars would need to withstand radiation, micrometeorite impacts, extreme temperature variations. It would need to be robust, possibly with self-repair capabilities. And if it had any active systems, power generation, propulsion, instrumentation, those systems would generate heat. They might also emit radiation across various wavelengths. When the probe approaches a star, it might activate certain systems, deploy sensors, adjust orientation. Any of those activities could produce observable signatures. The color change and brightness increase of 3I Atlas could be the probe activating as it enters the inner solar system, exactly the region of maximum interest for studying a planetary system. The high temperature could be waste heat from onboard systems, perhaps a nuclear power source or even something more exotic. The fact that the object maintains structural integrity at these temperatures could indicate advanced materials, perhaps carbon composites or metallic alloys far beyond our current technology. It sounds like science fiction, but it's actually just engineering. Advanced engineering, certainly, but not physics-defying. Just physics we haven't mastered yet. Most scientists push back hard against this interpretation, and they have good reasons. The principle of Occam's razor suggests we should prefer the simplest explanation that fits the facts. Extraordinary claims require extraordinary evidence, and so far the evidence, while anomalous, doesn't definitively prove artificial origin. Dr. Alan Stern, principal investigator of the New Horizons mission and an expert in Kuiper Belt objects and small solar system bodies, would likely argue that nature is weird and diverse, and we've only explored a tiny fraction of the types of objects that exist in the universe. Just because 3I Atlas doesn't behave like comets we've studied doesn't mean it's artificial. It might just be a different kind of natural object, formed under different conditions in a different star system, made of materials or structures we haven't encountered before. That's a fair point. The universe has surprised us repeatedly. Pulsars, when first discovered, were so regular they were briefly considered as potential alien signals, until we realized they were rotating neutron stars. Fast radio bursts seemed inexplicable until we started to understand their natural origins. Nature can be strange without being artificial. But here's what they don't say in the papers, what you have to read between the lines to understand. The scientific community is actually taking the artificial hypothesis more seriously than public statements suggest, not because they believe it's true, but because it's now considered a legitimate question worth investigating. In October 2020, NASA established a framework for evaluating potential technosignatures, signatures of extraterrestrial technology. In 2021, Harvard's Galileo project, led by Loeb, was founded specifically to search for evidence of extraterrestrial technological artifacts. Major universities and research institutions are allocating resources to this question. The Pentagon has released official reports on unidentified aerial phenomena. The scientific zeitgeist has shifted. The question is no longer, could there be aliens? But rather, how would we recognize them if they're here? And that's the lens through which 3I Atlas is now being viewed. Not as definitely artificial, but as potentially worth investigating with that possibility in mind. That subtle shift in perspective is huge. It means that when Loeb publishes his analysis of the October 29th data and raises the possibility of artificial origin, he won't be dismissed as quickly as he might have been even 5 years ago. The conversation has changed. The next critical window is already here, actually. 3I Atlas is currently moving outward from the Sun, heading back toward interstellar space. Its brightness should be declining as it moves away. The spectral characteristics should be reverting as the thermal environment changes. Every major observatory with the capability is tracking it. The Hubble Space Telescope has allocated observing time. The James Webb Space Telescope, with its infrared capabilities, is being pointed at this object to capture detailed spectral data. The European Southern Observatory's Very Large Telescope in Chile, one of the most advanced ground-based telescopes in the world, is collecting nightly observations. Radio telescopes, including the Very Large Array in New Mexico and the Arecibo successor facilities, are listening for any electromagnetic emissions from the object. The idea is to gather as much data as possible while 3I Atlas is still relatively close and bright enough to study in detail. Within weeks, possibly by late November 2025, the object will have faded significantly as it moves past Earth's orbit. By December, it will be difficult to observe. By early 2026, it will be beyond the asteroid belt, receding into the outer solar system and eventually back into interstellar space. This is a narrow window, and astronomers know it. Several key questions are driving these observations. First, will the spectrum continue to shift, or will it stabilize? If the blue shifted spectrum persists even as the object moves away from the Sun and should be cooling, that would be powerful evidence of an internal heat source. If it reverts to a more normal comet-like spectrum, that would support some kind of transient solar heating explanation, even if the mechanism remains unclear. Second, are there any periodic variations in the brightness or spectrum? If the object is rotating, and if it has different properties on different sides, we should see periodic changes. Those changes could tell us about the object's shape, composition, and whether there are any discrete features like vents, panels, or other structures. Third, is there any evidence of mass loss? Comets lose mass as they approach the Sun. Gas and dust are blown away by solar radiation and the solar wind. If 3I Atlas is a comet, even a weird one, we should be able to detect this mass loss, see the coma, and possibly a tail. If there's no detectable mass loss, or if the amount is far less than expected, that would be another anomaly to explain. Fourth, are there any chemical signatures in the spectrum that don't fit natural explanations? Certain elements or compounds, particularly refined metals or complex organic molecules, might hint at artificial processing. This is a long shot, but spectroscopy can reveal a lot about composition. Actually, let me correct that last point. It's not that specific molecules would definitively prove artificial origin. Nature produces complex chemistry, but certain patterns might be suggestive. For instance, if the spectrum showed emission lines from pure refined metals like titanium or chromium in proportions that don't match any known natural process, that would be interesting. Or if there were signatures of synthetic compounds, things that require industrial processes to create. Dr. Sarah Seeger from MIT, a pioneer in exoplanet spectroscopy and the search for biosignatures, has pointed out that detecting technosignatures is fundamentally about looking for patterns that nature doesn't easily produce. It's about probability and context. One anomalous spectral line might be a fluke. Multiple anomalous features, in combination, become harder to dismiss. That's what researchers are looking for in the 3I Atlas data. Not a single smoking gun, but a preponderance of evidence that tips the scales toward one explanation or another. For context, let's consider what a real interstellar probe might look like if a civilization were to build one. Breakthrough Starshot, an initiative founded by Yuri Milner and backed by scientists including Stephen Hawking before his death, is designing exactly this kind of probe. The concept involves a small, lightweight craft, probably weighing just grams, attached to a large reflective sail. A powerful laser array on Earth would blast the sail with photons, accelerating the craft to 20% of light speed. At that velocity, it could reach Alpha Centauri in about 20 years. The probe would carry miniaturized instruments, cameras, spectrometers, communication equipment. It would be powered by a tiny onboard energy source, possibly radioactive decay or stored energy. Now that's a human design concept, limited by our current technology. An advanced extraterrestrial civilization, one even a few centuries ahead of us technologically, could do far better. They might use materials we haven't invented, power sources we haven't imagined, propulsion systems based on physics we don't fully understand yet. The point is, an interstellar probe is not only possible, it's plausible. And if such a probe were passing through our solar system, how would it appear to our telescopes? It might look exactly like a small asteroid or comet, until it did something unusual, something that revealed its artificial nature. The practical applications of this discovery, assuming we can figure out what 3I Atlas actually is, are profound. If it's a natural object with exotic properties, understanding those properties could revolutionize materials science. Imagine materials that can withstand temperatures exceeding the sun's surface without melting or degrading. Imagine volatiles, or chemical compounds that exist in stable forms under conditions we thought impossible. The technological applications would span everything from spacecraft design to energy generation to industrial processes. If, on the other hand, 3I Atlas is artificial, the implications are even more staggering. Confirmation of extraterrestrial technology would be the most significant discovery in human history. It would answer fundamental questions about our place in the universe. It would also raise urgent new questions. Who sent it? What is it doing? Is it still active or is it a derelict? Could we intercept it and study it up close? And most importantly, should we attempt to communicate? And if so, how? There's actually a growing movement among scientists and engineers to develop a rapid response capability for interstellar objects. The idea is simple. When something like Oumuamua or 3I Atlas appears, we currently just watch it with telescopes as it passes through. We gather remote sensing data, but we don't interact with it. We don't send a spacecraft to intercept it, even though that would give us far more information. The reason is practical. Interstellar objects move fast, and they're usually discovered when they're already close to the sun and about to leave. By the time we could design, build, and launch an intercept mission, the object would be gone. But several groups, including the Initiative for Interstellar Studies and Loeb's Galileo project, are advocating for pre-built, ready-to-launch probes that could be deployed quickly when a target of interest appears. These probes would be small, fast, equipped with cameras and basic instruments, and designed for rapid deployment. Think of them as emergency response spacecraft. The technology exists. What's needed is funding and institutional will. If 3I Atlas turns out to be genuinely anomalous, if the case for further investigation becomes compelling, that might be the catalyst to make such a program reality. Public participation is actually possible here, in a limited but real way. Several citizen science projects aggregate data from amateur astronomers. If you have a telescope and a CCD camera, you can observe 3I Atlas and contribute your photometric measurements to databases like the Minor Planet Center or the Asteroid Light Curve database. Professional astronomers actually rely on this amateur data to fill gaps in coverage and provide continuous monitoring. Moreover, the computational analysis of spectroscopic data is increasingly being crowdsourced. Platforms like Zooniverse have hosted projects where volunteers help classify spectra, identify anomalies, and flag interesting targets for professional follow-up. There's even talk of using distributed computing networks, similar to SETI at home, to process the vast amounts of data that will be collected from 3I Atlas. So if you're scientifically inclined and want to be part of this investigation, there are avenues to contribute. Let's place this event in the context of science history because understanding how we got here matters. The search for life and intelligence beyond Earth has a long, often frustrating history. In the 1960s, the Drake equation gave us a framework for estimating the number of communicative civilizations in our galaxy, but it depended on parameters we didn't know. In the 1970s and 80s, SETI efforts scanned the skies for radio signals, finding none. In the 1990s, the first exoplanets were discovered, proving that planets around other stars are common. In the 2000s, missions like Kepler revealed that Earth-like planets are abundant. In the 2010s, we started to study exoplanet atmospheres, looking for biosignatures. And now in the 2020s, we're encountering interstellar objects and asking whether they might be artificial. Each decade has brought us closer to answering the question. The discovery of Oumuamua in 2017 was a watershed moment because it was the first confirmed interstellar object, proving that material from other star systems does pass through our solar system. Before that, it was theoretical. Now it's observational fact. 2I Borisov confirmed it wasn't a one-time fluke. And 3I Atlas, with its bizarre behavior, is pushing the question further. History teaches us that paradigm shifts in science often come from unexpected observations, things that don't fit the prevailing model. Continental drift was dismissed for decades until evidence accumulated. Black holes were theoretical curiosities until we detected them. Exoplanets were speculative until we found thousands. The idea that interstellar space might contain artificial objects from other civilizations is currently at that threshold of respectability. And 3I Atlas might be the observation that tips it over. Here's another piece of the puzzle that deserves attention. Something the preliminary reports mention but don't emphasize. The consistency of the effect. The spectrum didn't just shift once and stabilize. According to the timeline from Zhang and Badams, the shift was ongoing over the observation period of October 28-29. It was a dynamic process, a progression. That's important. If this were a one-time event, maybe a collision with a micrometeorite that vaporized material and created a temporary bright flash, you'd expect a brief spike and then a return to normal. If it were a structural failure, a fragmentation event, you'd expect a sudden change followed by either gradual fading or chaotic behavior. But a progressive, steady shift suggests a process that's unfolding over time, something with momentum and continuity. Researchers who've glimpsed the raw data are tight-lipped, but the implication is that whatever is happening to 3I Atlas isn't random or instantaneous, it's a progression. And that makes it harder to explain with catastrophic or stochastic processes. It looks more like a system responding to changing conditions, like a mechanism engaging. Dr. Gregory Laughlin, an astronomer at Yale who studies exoplanets and orbital dynamics, would probably point out that there's another layer to consider: the timing. 3I Atlas exhibited this dramatic change right at perihelion, the moment of closest approach to the Sun. That's not a coincidence. Whatever the mechanism, it's triggered by solar proximity, by the intense radiation environment, by the thermal and electromagnetic conditions near the Sun. For a natural comet, that makes sense. Peak solar heating causes peak activity. But for the level of activity observed, for the specific spectral signature, natural processes seem inadequate. For an artificial probe, the timing would also make sense. If you're going to activate systems, you do it when you're passing through the most interesting part of a planetary system, the region where planets form and where life is most likely. You'd want to gather data on the star itself, on the inner planets, on conditions in the habitable zone. The timing fits both natural and artificial scenarios, but the details of what's observed favor the artificial interpretation. That's the maddening thing about this case. Every piece of evidence has multiple explanations, but when you combine them, the natural explanations require increasingly contrived assumptions, while the artificial explanation, though seemingly outlandish, remains consistently plausible. Now, about that temperature measurement, that word temperature is doing a lot of work there. When Loeb calculates that the object's temperature may exceed the sun's surface, he's specifically talking about brightness temperature or color temperature, the temperature you'd infer from the spectral distribution, assuming the object is a perfect blackbody radiator. But real objects aren't perfect black bodies. They have emissivity less than 1.0, meaning they radiate less efficiently than an ideal black body at the same temperature. They also have reflectivity, absorbing some wavelengths better than others. So the actual physical temperature of the object's surface might be different from the inferred temperature. It might be cooler but with selective emission that mimics a hotter black body. Or it might be hotter in localized regions while cooler overall, creating a composite spectrum that appears very hot. The point is, the temperature calculation is based on a model. And if the model assumptions are wrong, the conclusion is wrong. However, and this is critical, the standard models for comets already account for emissivity and reflectivity. Cometary ices and dust have well-studied optical properties. When those properties are plugged into the models, you get predictions. And 3I Atlas is exceeding those predictions by enormous margins. So even accounting for uncertainties in the model, something is fundamentally off. Let's bring this back to the core mystery. We have an object from beyond our solar system. It approaches the sun. It gets brighter, much brighter than expected. Its spectrum shifts blue. Its inferred temperature becomes impossibly high. It doesn't fragment or behave like any comet we've seen. And it does all this in a consistent, progressive manner over multiple days. That's the observational reality. Now, the interpretations divide into two broad camps. Camp 1, natural but exotic. Maybe it's a comet from a star system with very different chemistry, where ice is formed under unusual conditions and have different properties. Maybe it's a fragment of a disrupted planet or moon, with exposed metallic core material that's reacting with solar radiation in unexpected ways. Maybe it's a new class of object we've never encountered, something the universe produces rarely and under special circumstances. This camp argues we need more data, better models, and patience before jumping to extraordinary conclusions. Camp 2, artificial or influenced by intelligence. Maybe it's a probe, active or derelict. Maybe it's a craft from another civilization, malfunctioning or activating. Maybe it's something we don't have a framework to understand yet, but that's designed rather than natural. This camp argues that the sheer accumulation of anomalies, the failure of natural models to account for observations, and the specific nature of the behavior all point toward intentional design. The philosophical implications of this discovery, regardless of which interpretation is correct, are profound. If 3I Atlas is natural, it tells us that the universe contains far more diversity than we've imagined. It tells us that our models of planetary formation, cometary science, and stellar system evolution are incomplete. It humbles us by showing that even in our own cosmic backyard, nature can produce things we don't understand. That's actually a comforting thought in a way. The universe is still full of wonders, still capable of surprising us. If 3I Atlas is artificial, it tells us we're not alone. It tells us that intelligence arises elsewhere in the universe, that it develops technology, that it explores. It raises the possibility of contact, of communication, of learning from civilizations far older and more advanced than ours. It also raises existential questions. What are their intentions? Are we safe? Are we relevant? Do we even have the cognitive framework to understand their goals? The history of human contact between disparate cultures is not always encouraging, but it's also led to exchange of knowledge, to growth, to expansion of horizons. The implications go beyond science. Philosophy, religion, sociology, politics, all of human thought would have to grapple with the reality that we're not unique. Let me shift gears and talk about the skeptical position in more detail, because it's important to understand why most scientists remain unconvinced of the artificial hypothesis despite the anomalies. The core of scientific skepticism isn't closed-mindedness, it's a demand for rigor. Science advances by testing hypotheses against evidence, and extraordinary hypotheses require extraordinary evidence. The artificial hypothesis is extraordinary because it invokes an entity we've never confirmed: extraterrestrial intelligence. Until we have direct, unambiguous evidence of such intelligence, invoking it to explain anomalies is seen as premature. Dr. Phil Plait, an astronomer and science communicator, often emphasizes that unexplained doesn't mean alien. It just means we don't understand it yet. History is full of natural phenomena that once seemed inexplicable, but eventually yielded to scientific investigation. Ball lightning, giant squid, rogue waves. These were all considered mythical or impossible until we developed the tools and knowledge to study them. The skeptical position on 3I Atlas is that we're seeing something we don't yet understand, but that patience and better data will eventually reveal a natural explanation. And that's a reasonable position. It's consistent with the scientific method. It's how we should approach anomalies. But, and here's the thing, skepticism can also become dogma. If we rule out hypotheses a priori, if we declare certain explanations off limits regardless of evidence, that's not skepticism, that's bias. And there's an argument to be made that the scientific community has been biased against seriously considering artificial origins for interstellar objects, not because the idea is implausible, but because it's uncomfortable and because the field of SETI has been stigmatized for decades. That's changing, slowly. The establishment of NASA's techno-signature framework, the founding of the Galileo project, the publication of papers in mainstream journals discussing the possibility of artificial objects in our solar system, all of these represent a thawing of the previous taboo. So when Loeb publishes his analysis of 3I Atlas and seriously entertains the artificial hypothesis, he's not being a crank. He's being a scientist willing to follow the evidence wherever it leads, even if it leads to uncomfortable places. Whether he's right or wrong, whether 3I Atlas turns out to be a weird comet or something more, the fact that the question can be asked and investigated is progress. Speculation time. Let's say hypothetically that 3I Atlas is indeed an artificial probe. What might it be doing? If it's active, it's presumably collecting data. It's observing the sun, the planets, the asteroid belt, the structure and dynamics of our solar system. It might be measuring stellar properties, looking for signs of technological civilization, assessing the habitability of Earth and other worlds. If it has communication capabilities, it might be transmitting data back to its origin, though we likely wouldn't detect that transmission unless it was directed at us, or unless we happen to intercept the beam. If it's autonomous, it's making decisions based on programming or even artificial intelligence. The activation at perihelion could be a pre-programmed sequence: approach star, activate sensors, collect data, transmit, continue trajectory. If it's derelict, if it's no longer functioning as designed, what we're seeing could be a malfunction, systems overheating, or failing in unexpected ways. That could actually explain the anomalous temperature, a power system running out of control, shedding energy as heat and light. Or we could be witnessing the probe's end-of-life sequence, a self-destruct or intentional deactivation. These are all plausible scenarios if the artificial hypothesis is correct. Alternatively, let's say 3I Atlas is natural but composed of materials or structures we haven't seen before. What might those be? One possibility: metallic hydrogen or other exotic forms of matter. Under extreme pressure, hydrogen can become metallic, and theoretical models suggest it might remain metastable at lower pressures under certain conditions. If 3I Atlas contained significant amounts of metallic hydrogen, and if that hydrogen was transitioning back to normal molecular hydrogen as it warmed near the Sun, the energy release could be enormous. Metallic hydrogen is predicted to store energy like a spring. Releasing that energy could create intense heat and light. This is highly speculative, but it's at least grounded in known physics. Another possibility: the object could be a fragment of a disrupted terrestrial planet from another star system. If a planet were shattered by a collision or tidal disruption, fragments of its iron core could be ejected into interstellar space. An iron-rich object, heated by the Sun, could potentially reach high temperatures and exhibit unusual spectral properties. Iron's melting point is 1811 Kelvin, and it glows red-hot well below that. If the object were mostly iron, subjected to intense solar radiation, maybe it could reach temperatures in the thousands of Kelvin. But getting to 5,000 Kelvin or higher would require more than just passive heating. You'd need active energy input or release, and it's unclear what natural mechanism would provide that. Actually, let me correct that. There is one natural mechanism that could produce extreme heating: impact. If 3I Atlas collided with a small object, even a grain-sized meteoroid, at interstellar velocities, the kinetic energy released would be enormous. At speeds of tens of kilometers per second, a gram-sized projectile carries the kinetic energy of several sticks of dynamite. The impact would vaporize both the projectile and part of 3I Atlas's surface, creating a flash of intense heat and light. Could that explain the observations? Possibly, if the timing was right and if the impact occurred just as Zhang and Badams were observing. But impacts are instantaneous events. The heating and emission would last seconds to minutes, not days. The progressive change observed over October 28-29 doesn't fit an impact scenario. Unless there were multiple impacts, a barrage of particles, but that's astronomically unlikely. Space, even interstellar space, is mostly empty. So while impact is a valid consideration, it doesn't seem to fit the data. Here's where things get really strange. And this is information that's being discussed in private but hasn't been widely publicized yet. According to sources within the observational astronomy community, there are additional data on 3I Atlas that haven't been released because researchers are still trying to verify and understand them. I can't confirm this directly, but the rumors suggest that there may be evidence of periodic brightness variations with a very short period, on the order of minutes to hours, which could indicate rapid rotation or pulsation. There may also be hints of polarization in the light, meaning the light waves are aligned in a particular direction, which can occur when light reflects off smooth surfaces or passes through aligned particles. If true, these details could be crucial. Rapid rotation could explain some thermal effects through centrifugal forces or differential heating. Polarization could tell us about the object's surface texture or the nature of any surrounding material. But these are unconfirmed reports, and we need to be cautious about reading too much into them. The formal scientific papers, when they're published, will present the verified data. Until then, it's all preliminary and subject to revision. The question everyone's asking, the question that underlies all of this, is simple. What is truth? How do we know what's real? In science, truth is provisional. We build models based on observations. We test those models with experiments and further observations, and we revise them when they fail. The scientific method is powerful because it's self-correcting, but it's also slow. It requires patience, rigor, replication. In cases like 3I Atlas, where the object is transient and the observations are difficult, We're forced to make judgments based on incomplete data. We're forced to weigh competing explanations without definitive proof for any of them. And that's uncomfortable. We want answers. We want certainty. But the universe doesn't owe us easy answers. Sometimes the truth is ambiguous. Sometimes we have to live with uncertainty while we gather more information. That's where we are right now with 3i Atlas. We have observations that don't fit standard models. We have competing hypotheses, none of which fully explain the data. And we have a narrow window to gather more information before the object recedes beyond our reach. Stop and consider that. Right now, as you read this, 3i Atlas is moving through space at roughly 40 kilometers per second. Every hour, it travels about 144,000 kilometers, more than a third of the distance from Earth to the Moon. Every day, it moves about 3.5 million kilometers farther from the Sun. In a week, that's 24 million kilometers. In a month, over 100 million kilometers. By mid-November, it will be near Earth's orbit. By December, it will be approaching Mars's orbit. By January 2026, it will be in the asteroid belt. By mid-2026, beyond Jupiter. By 2027, in the outer solar system. By the 2030s, exiting past the Kuiper belt. And by the 2040s, it will be back in interstellar space, receding into the vast dark between stars, forever beyond our reach unless we develop propulsion technology far beyond our current capabilities. This is a fleeting opportunity. We have one chance to study this object up close, and that chance is now. If we fail to gather sufficient data, if we fail to answer the key questions, we may never get another opportunity. That urgency is driving the observational campaign. That urgency is why astronomers are working around the clock, why telescope time is being reallocated, why resources are being marshaled. They know this matters. Let's talk about the broader context of what this means for humanity. For the entirety of human history, we've wondered if we're alone in the universe. Every culture, every civilization has looked at the stars and asked that question. Are there others? Are we unique? The answer has profound implications for how we see ourselves, for our philosophies, our religions, our sense of purpose. If we're alone, if Earth is the only place where life and intelligence arose, then we bear an enormous responsibility. We're the universe's way of knowing itself, in Carl Sagan's phrase. Our survival, our flourishing, our eventual spread to other worlds becomes cosmically important. If we're not alone, if intelligence is common, then we're part of a larger community, a galactic ecosystem of minds. Our importance becomes relative. We're one species among many, one civilization among countless others. Both possibilities are profound. And 3i Atlas sits at the nexus of this question. If it's natural, the question remains open. But we've learned that nature is stranger than we thought. If it's artificial, the question is answered. We're not alone. And the universe is inhabited by minds that build and explore. Either way, we're at a pivotal moment. The mystery deepens when you consider the trajectory. 3i Atlas didn't just randomly wander into our solar system. Its path brought it through the inner solar system, past the Sun, through the region where Earth and the terrestrial planets orbit. That's not the most likely trajectory for a random interstellar object. Most interstellar objects, coming from random directions with random velocities, would pass through the outer solar system. Maybe the asteroid belt, but not necessarily the inner system. The fact that 3i Atlas came close to the Sun, close enough for perihelion at 0.3 AU, is somewhat unusual. Not impossible, not even highly improbable, but unusual enough to notice. If it were a probe, if it were deliberately aimed, the trajectory makes perfect sense. You'd target the inner system to study the star and any habitable worlds. If it's natural, the trajectory is just one of many possible paths. And we're noticing it because it happened to come close enough for us to detect and study. Again, the evidence is ambiguous. It fits both scenarios. Dr. Avi Loeb himself has a reputation that colors this entire discussion, and it's worth addressing. Since Oumuamua, Loeb has been outspoken about the possibility of extraterrestrial technology. He's written a book, Extraterrestrial, the first sign of intelligent life beyond Earth, arguing that Oumuamua's acceleration was best explained as a light sail. He's founded the Galileo Project to search for technological artifacts. He's given countless interviews and written numerous op-eds. Some in the scientific community view him as a brave maverick, willing to ask uncomfortable questions and challenge consensus. Others view him as overly speculative, too eager to jump to exotic conclusions, too focused on publicity. The truth is probably somewhere in between. Loeb is a serious scientist with an impressive publication record and significant contributions to astrophysics. He's also someone who clearly believes that the search for extraterrestrial intelligence is one of the most important scientific endeavors we can undertake, and he's willing to spend his reputation on it. When he analyzes 3I Atlas and suggests it might be artificial, that suggestion carries weight because of his credentials, but it's also scrutinized more critically because of his advocacy. That's the nature of science. Arguments are judged both on their merits and on the credibility of those making them. Ideally, only the former would matter, but in practice, both do. The final perspective, bringing everything together, requires us to return to the beginning. Something impossible is happening. An object from beyond our solar system is exhibiting behavior that defies our models. It's hotter than it should be, brighter than it should be, stranger than it should be, and we're scrambling to understand it before it disappears forever. In the days since October 29th, when the anomalous data became public, the scientific community has mobilized. Observatories worldwide are tracking 3I Atlas. Theorists are working on new models. Data analysts are combing through the spectroscopic observations, looking for details, for patterns, for clues. And the public, those who are paying attention, are watching with a mixture of excitement and trepidation. Could this be it? Could this be the confirmation that we're not alone? Or will it turn out to be another natural phenomenon? Fascinating in its own right, but not paradigm-shifting? We don't know yet. And that not knowing, that uncertainty, is both frustrating and exhilarating. What we've learned is that the universe still has the capacity to surprise us. We've mapped the cosmic microwave background, detected gravitational waves, imaged black holes, discovered thousands of exoplanets. We've probed the depths of space and the smallest scales of quantum mechanics. And yet, a single small object, no more than a kilometer across, can confound us, can challenge our understanding, can make us question fundamental assumptions. That's a humbling reminder that for all our progress, we're still at the beginning of understanding the cosmos. We're still explorers in a vast, largely unknown territory. And that's as it should be. A universe fully understood would be a universe drained of wonder. A cosmos with no more mysteries would be a sad place indeed. What remains a mystery, what will likely remain a mystery even after all the data is analyzed and all the papers are published, is the ultimate question of intent and meaning. If 3I Atlas is artificial, why was it sent? What is its purpose? Is it part of a network of probes exploring the galaxy? Is it a one-off mission from a long-dead civilization? Is it even aware of us, or are we incidental to its mission? These questions may be unanswerable with remote observations alone. To truly know, we'd need to intercept the object, study it up close, perhaps even retrieve it. And that's beyond our current capabilities, though not beyond the realm of possibility for the near future. The technology to launch a fast intercept mission exists. What's needed is the will and the resources. If 3I Atlas proves sufficiently anomalous, if the case for investigation becomes compelling enough, that mission might happen. Perhaps not for this object, which will soon be beyond reach, but for the next one. There will be a next one. Interstellar objects pass through our solar system regularly. We're just beginning to detect them. As our observational capabilities improve, as survey telescopes like the Vera Rubin Observatory come online and scan the sky nightly, we'll find more. And one of them might be the definitive case that demands closer study. The forward-looking conclusion is this: we're entering a new era of astronomy, one where interstellar visitors are no longer theoretical, but observable and potentially accessible. These objects are windows into other stellar systems, messengers from distant parts of the galaxy, possibly even artifacts of other civilizations. Each one that passes through is an opportunity to learn, to gather data, to test hypotheses. 3I Atlas, with its bizarre behavior and its challenge to conventional models, is accelerating this transition. It's forcing us to take interstellar objects seriously, to allocate resources to their study, to consider possibilities we've previously dismissed. Whether it's a weird comet or a probe from another world, it's already served a purpose. It's made us think, made us question, made us wonder. And in the end, that's what science is about. Not having all the answers, but asking the right questions. Not knowing everything, but being willing to explore, to investigate, to follow the evidence, even into uncertain territory. The philosophical note on knowledge, the place where this story ultimately leads, is that understanding is a journey, not a destination. Every answer generates new questions. Every mystery solved reveals deeper mysteries. 3I Atlas, whatever it ultimately proves to be, is a single step on that endless journey. It's a reminder that the universe is vast, complex, and full of phenomena we don't yet understand. It's a challenge to our current models and a spur to develop better ones. It's a glimpse of possibilities that until recently belonged only to science fiction. And it's a call to remain curious, to stay humble, to never assume we've learned all there is to learn. The stars are still out there, full of secrets. Objects like 3I Atlas are still passing through our cosmic neighborhood, carrying information from places we've never seen. And we're still here, watching, wondering, trying to decode the messages the universe sends us. That's the true story of 3I Atlas. Not just the mystery of one anomalous object, but the larger story of humanity reaching out into the cosmos, driven by an insatiable curiosity to know what's out there, who's out there, and what it all means. The data will continue to come in. The analyses will be published. Debates will rage in scientific journals and conferences. And somewhere out there, 3I Atlas will continue its journey, indifferent to our questions, carrying its secrets back into the void. But we'll remember it, we'll study it, and we'll be better prepared for the next visitor, the next mystery, the next opportunity to glimpse the truth about our universe and our place within it.